Chapter 12 of our text ends by providing some general guidelines for tuning and troubleshooting feedback control loops. For flow control, the process dynamics are usually fast. That is, they have relatively small time constants. Often the largest time constant is simply the actuation of the valve, and these can have negligible time delays. Disturbances are usually small amplitude, high frequency noise associated with things like turbulence in the flow measurement or vibrations from a pump, etc. For most flow control operations, PI control is suitable. When controlling temperatures, often process dynamics are slow. That is, they have large time constants and may have time delays. This is sort of the opposite of the conditions for flow control. Typically, PID control is used to speed up the process dynamics for temperature control loops. For level control, it depends. Like flow control, level measurements can be noisy due to things like turbulence or agitation in a tank. Therefore, the derivative element is often not used. Surge tanks can tolerate some deviation from the set point, but should avoid abrupt changes in the outlet flow rate. In fact, often the purpose of a surge tank is to accommodate level changes to decouple downstream processes from upstream processes. So we want the surge tank level to vary. Proportional only control may be sufficient. Chemical and bioreactors may require very tight control of the liquid level to maintain constant residence time. In this case, PI control should be used to eliminate steady-state offsets. When combined with energy balances, level control gets complicated and might require strategies that we have not talked about yet, but that we'll get to later on in the semester. For pressure control, process dynamics are also usually very fast, similar to flow control. That is, they have small time constants with negligible time delays. PI control can be used with a small integral element, that is, a large value of tau I. For composition control, process dynamics may have large time delays associated with sampling, measurements, and mixing. Often this also requires advanced control strategies that we will talk about later on in the semester. Controller tuning cannot solve every control loop problem. If some other component of the control loop is malfunctioning, for example, a sensor isn't working, then changing a controller setting won't fix it. Common problems in control loops that should be addressed before attempting to change controller settings include things like sensor failure or valve actuation and positioning. Sometimes a valve needs to be serviced if it's sticking. Or process changes, such as changes in the throughput or regeneration of a catalyst or equipment upgrades and repairs. Sensor failure can usually be easily diagnosed by a zero measurement or no measurement variability when you expect the measurement to be varying. To diagnose valve problems, you should put the controller in a manual mode and change the controller output to see if you get a corresponding flow rate change, or if that flow rate change doesn't behave as expected. If there have been process changes, these of course should be documented, and if that's the case, then often the controller does indeed need to be retuned. Process changes include things like replacing, upgrading, or repairing equipment. To summarize the topics we discussed from Chapter 12, we initially described some important controller design criteria. These involve trade-offs. For example, we can design controllers to be very stable or very robust. We can design controllers to reject disturbances or track set points very well. We can design controllers to avoid excessive controller action or to avoid steady-state offset. The model-based design criteria such as the direct synthesis and IMC methods and tuning relations are recommended, but these usually require some kind of model for the process. When the direct synthesis or IMC methods are used to define controller tuning parameters for lag-dominant models, they sometimes need to be modified. We talked about using the integral approximation and the Skogestad modification of the IMC method. Although we have many different tuning relations that are introduced in this chapter, they have some similar features, such as calculating a gain that's in general inversely proportional to the gains of the other elements of the control loop. The control strategy chosen, for example, proportional, PI, or PID control, can be guided by the type of control loop. Online tuning and troubleshooting can be used to improve controller performance. Online tuning by the continuous cycling method, although it is recommended by some controller manufacturers, may not be a good idea for many types of control loops. This is one of the least efficient methods for controller tuning, and often other strategies are much more useful.